All right, so we want to make a mathematical model for the wind-driven circulation of the subtropical gyres, and we're going to think about the subtropical gyre in the Atlantic for this example. All right, so what's the subtropical gyre? Well, if this is the Earth, this is the equator, and then you put in the continents, over here North America, over here Africa, and Europe, and if you look between latitudes of about 15 degrees north to about 45 degrees north, in this range, there's what's called the gyre, and it's a current that flows roughly like this. So there's a strong northward current on the western boundary and a kind of a slower return flow in the interior. So it kind of circulates around in a gyre like that. That's what we call the subtropical gyre. So the name of this current on the western side here, there's very strong western boundary current. In the Atlantic is the Gulf Stream. So this is the Gulf Stream. Gulf Stream. It's an example of a western boundary current. And its speed, the typical velocity, V, is about 1 meter per second for the western boundary current. In the interior, the flow that flows south, this is, we know it, physical oceanographers call this, this southward drift called the Sverdrup balance, or the Sverdrup flow. Sverdrup flow, in honor of Sverdrup, who was the first one to come up for the theory of why there is this southward flow. And that current, V, is on the order of 1 or 0.1 meters per second, so about 10 centimeters per second, so about 10 times faster on the west than on the north. These are scales. So in this lecture, when we mention the velocity vector v, we'll write it in terms of Cartesian coordinates u, v, and w, where this is the eastward, northward, and upward velocity components. Or the x, y, and z components. X, y, and z. East, north, up. All right, so v, the big V, is the typical scale for this velocity v. All right, so what's the size of the gyre? Well, the north-south extent of this gyre, from here to here, that's about 30 degrees of latitude, and it's about 100 kilometers per degree, so that's about 3,000 kilometers. So Ly is roughly equal to 3 times 10 to the 6 meters, right? 3,000 kilometers, 1,000 meters per kilometer is 3 times 10 to the 6. The east-west extent for the Atlantic from here to here, let me put it in red. This would be Lx, and it's a little bit bigger, maybe 5,000 kilometers, but it's roughly the same size as Ly. So for our mathematical model, we're going to assume, we're just going to take a square, base it in Cartesian, and we're going to take it in Cartesian coordinates. So it's true that there is a sphericity and the Earth is curved, but to make the mathematical model simple, we're going to assume that there's not enough variations due to curvature that we can neglect it. And we do that to make the physics as simple as possible, to grab the essence of what's going on, not to get the most accurate answer necessarily. And so the width of this boundary current here, we can measure the width, go out in a ship and measure the width, or measure the current. But the important part is that all the mass that flows southward in the interior, in this Sverdrup flow, is going to be returned northward in the western boundary current, in a northward flow. So what we have is a narrow but intense current flowing north, carrying as much mass northward as there is flowing southward at a more leisurely pace everywhere else in the gyre. And so that there is no net accumulation of mass either to the north or to the south. If there was, and we're thinking about climate timescale, long timescales, then eventually the sea level would have to drop if there was more flow southward, drop in the north, increase in the south, or vice versa. So these two have to balance on time scales of longer than a few days. They have to roughly be the same. You can't just accumulate a whole bunch of mass to the north or south. Right, so the eastward velocity, the scale of this velocity is roughly the same as the scale of the v velocity by mass balance. So these two, u and v, U and V are roughly U, which is about equal to, we're going to take that to be 0.1 meters per second for everywhere in the interior, not for the western boundary current. If we were doing the western boundary current, U would be of order 1 meter per second. So that's for the spherically balance in the interior. W, on the other hand, that one is much smaller. And in fact, we can't measure that one directly. So the currents are so small that if we put a current meter out and try to average over all the gravity waves and the tides, the actual signal would be lost in the noise. So the current meters are not accurate enough to measure W on these large scales. But we can calculate it using something called the Ekman balance, which I'm going to talk about next. But it turns out to be about 100 meters per year. So in about a year of the Ekman, which is convergent, Ekman flow, which is convergent in the gyre, will pump water down about 100 meters in a year, roughly, of that order of magnitude. This is, this is W, and that's capital W is about 100 meters per year. Much, much smaller than this quantity, because there's a lot of seconds in a year. All right, so let's start building our theory. I'm going to write down the momentum equations. We're going to look at different balances between different terms, one called the geostrophic balance and the other one the Ekman balance. And we're going to talk about those now.